In this series, we're trying to build a vacuum tube computer, something I've dubbed the UE14500. UE obviously stands for Usagi Electric, and 14500 kind of harkens back to the Motorola MC14500, which is a little 1-bit microprocessor that we used as heavy inspiration. But we have made a few changes. The Motorola chip only has a logic unit, whereas now we have an arithmetic logic unit. We have the ability to do addition and subtraction. Now, in the previous episode, we had the instruction register and the decoder finished, and we started work on the interconnect, the piece that's going to kind of sit in between the top half and bottom half of the processor. That's going to connect the instruction register and decoder with the arithmetic logic unit and the input and output enable registers and all of those things. And we only got about halfway through building that interconnect. So what I want to do today is I want to finish out the second half of that interconnect. But the second half of that interconnect has a very important piece on it for being able to do subtraction. Like I said, I want our arithmetic logic unit to be able to do addition and subtraction. So we need to get all of the pieces in place to be able to enable those functions. And one of those is creating a very unique type of logic gate. So what I want to do today is I want to hop over to the bench, take a look at what kind of logic gate it is that we need to create to enable subtraction and why we need to create it, and then we need to build it. I'm going to test out a couple different designs before we build it. So let's hop over there and get started. All right, so here's the gate level diagram for the UE14500 that we're currently building up. And so far we've built the instruction register on the left here, along with the skip control that's going into it. We've built the instruction decoder and all of the buffers, and we've started to build a little bit of the interconnector. And the interconnect is going to have the input enable register and some of the logic that's required for our arithmetic logic unit. Now, looking at it in this form is very useful for figuring out how signals are moving throughout the system, but it is incredibly unhelpful when it comes to figuring out how we're going to physically build it. And so to that end, we have this little block diagram here. And this shows essentially the top half of the microprocessor plus the interconnects. And this is what we started working on in the previous episode. So we can see that we have our control for the input enable register as well as the input enable register itself and a little display for it. So today I want to finish off the rest of the interconnect. And you can see it includes an exclusive OR gate as well as some glue logic that's going to become important much later in the build. Now, everything that we've built up to now has had a pretty clear purpose, but suddenly out of nowhere we have this exclusive OR gate. And so this raises the question of why do we need an exclusive OR gate? And in order to understand what this gate is doing, we kind of need to take a step back and take a look at everything that we're trying to accomplish with the arithmetic logic unit. We're trying to do some logic operations, which are pretty self-explanatory. We're also trying to do addition, which we're going to achieve using a full adder. And we'll go into detail about how I'm going to build the full adder in a future episode when we get to actually building the full adder itself. But as well as addition, we're also trying to do subtraction. And in order to do subtraction, well, we're actually just going to end up doing more addition. And we're going to do that by doing what's called 2's complement. If you want to know more about how 2's complement subtraction works, you should definitely check out Ben Eater's stuff. He makes the most wonderful educational videos, and he has a great series on how to do subtraction using 2's complement. And so what 2's complement is we essentially just invert and add 1, and we're only inverting one of the operands. So for example, if we have 1010, which in this case is 10, and we want to subtract 0011, which is 3 from it, we get 0111, which is 7. 10 minus 3 is 7. So how do we do this using just hardware that is essentially built to only add numbers? Well, we can invert the smaller operand and then add 1 to it. So if we have 1010 minus 0011, we end up with 1010 plus 1100, 1100 being the inverse of 0011, and then we add 1 to that, 0001. 1. And you can see that the result comes out to 1, 0, 1, 1, 1. Now we ignore the carry bit, so we ignore that 1 that's on the far left, and then we get 0, 1, 1, 1, which just so happens to be the correct binary for subtraction. So by inverting the smaller operand and adding 1, we were able to get the correct answer for subtraction doing just addition. And the important part of this is that we need to invert one of the operands. So if we take a look at the logic diagram for our arithmetic logic unit, if we look at the addition, we've got a full adder, which is what this little box right here in the middle is. And the full adder has two operands coming into it, which are these two lines that are coming in from the left. We also have a carry in, which is coming in from the top. And we're going to use this carry in for our add 1. But we still need to invert one of the inputs that's coming into the side here. And that's where our exclusive OR gate comes in. In an exclusive OR gate, the output only goes high if one of the inputs is high. If both the inputs are low, or if both the inputs are high, the output is low. So what this means is that if we hold one input low, the other input can essentially pass through. So if input A is 0 and input B is 0, our output is 0. And if input A is 1 and input B is 0, our output is 1. So A is essentially passing through the exclusive OR gate. However, if we take our input B and put it at 1, the output is now going to be the opposite of input A. So if input B is 1 and input A is 0, the output is 1. But if input A now is 1, well, we have 1, 1 on the inputs, that means that the output is 0. So by using an exclusive OR gate, we can invert one of the inputs into our full adder depending on whether we're doing subtraction or addition. So this is how we can use an exclusive OR gate to enable us to do subtraction using just addition. So that's why we need to build the exclusive OR gate. But so far we've only built a handful of logic gates. We've built an inverter, we've built ORs, we've built NORs, and in the previous episode we built a NAND gate. But an exclusive OR gate is a whole new challenge to try and learn how to build. So there's a couple different ways to tackle this. And one way is to use very interesting diode logic. And so this is probably the most compact way to build an exclusive OR gate that I can come up with. We essentially have 4 diodes, and these diodes actually look somewhat like a full bridge rectifier, but we don't have any AC signals here, so we're not really using them like that. We're mostly using these actually in a pretty similar way to the way that we built the NAND gate. And so you can see that the 2 diodes on the right connect to the grid through a 220,000 ohm resistor, and then there's also a 1 meg resistor that's a pull up to 24 volts. If I turn both switches on, it blocks the negative 12 volts to essentially both diodes, which allows the grid to be pulled high through the 1 meg ohm resistor, which then allows the tube to conduct, which pulls our output low. Now here's where things get interesting. If we have just one of the input switches on, we want the output to go high. But if we have both of the input switches off, we want the output to go low. And so we're doing something interesting with the plate of the vacuum tube. We have our 33,000 ohm resistor that would normally go to plus 24 volts, instead coming all the way over and connecting up to these 2 diodes here. So what this means is that when both of the input switches are off, the plate is actually pulled low through this 220,000 ohm resistor to minus 12 volts. However, if one of the switches goes on, that's now 24 volts flowing through the diode over into the plate. So that's a very tricky way for us to get an exclusive OR output. Now I want to buffer that exclusive OR output, and I'm using that to try and counteract some of the major flaws that this design has, but the big flaw is that this works beautifully if I have a clean 24 volts coming in through my switches here. But maybe this isn't hooked up to source. Maybe this is an output from something else that isn't buffered. And so we can start running into essentially problems with what our plate output voltage is here. And so the cathode follower buffer helps counteract some of that. But to actually solve that problem properly, I would need to change this from a cathode follower buffer to an inverting amplifier to amplify whatever output it is that we're seeing here. But if I do that, we're no longer an exclusive OR, we're now an exclusive NOR. And then I need to reinvert that again to become an exclusive OR. But this is still a really cool design, and I want to give this a test. So let's pull the breadboard out real quick and just give this a test just for fun. All right, so we've got our exclusive OR gate set up on the breadboard here. We've got these two 6AU6s here standing in place of our 6DJ8 here. A lot of my schematics, you'll see that I use a 6DJ8. That's because I build my schematics in a program called Tina, and the vacuum tube model that I have imported into that is the 6DJ8. The Tina simulation performance of the 6DJ8 is actually surprisingly close to the real world performance of the 6AU6. And so what we have here is essentially identical to this schematic down here. The only difference is that since the 6AU6 is a pintode, we have a 100 ohm resistor that goes to the screen grid. Other than that, they're pretty much identical. And you can see that the 4 diodes over here are right here, set up in this kind of diamond pattern right up here. And then we have our 2 push buttons, and the exclusive OR output should be displayed on this LED here. Now, since this tube on the right here is a cathode follower buffer, it's just going to be showing pretty much exactly whatever the plate value is here. And when we first turn on the switch, the plate value is going to be pulled to minus 12 volts. So this LED should stay off. So let's go ahead and flip the switch and see what happens. Okay, our power is on. I can see the little red LED on our little buck boost converter back here. This is taking the 24 volts and dropping it to 6 volts for the heaters. And speaking of those heaters, they should be pretty warm by now. So if I push one button, we should see the LED turn on. Let's give that a shot. Yeah, that's awesome. Look at that. All right, let's try the other button. If I push the other button, the LED should turn on. Yeah, there we go. Okay, so we've got 3 out of the 4 states. The final state is to push both buttons and make sure that the LED stays off. Yeah. All right, so we saw the LED gives a slight flash there, and that's because I'm not pushing the buttons at exactly the same time. And that's just the nature of these buttons and the nature of me being a human. I mean, we can see that's working perfectly as an exclusive OR gate. That is awesome. I'm super happy with that. But like I mentioned before, I have some reservations about how the plate of this first tube here is set up. I mean, it's actually being pulled to minus 12 unless the input is coming in. And if this input is a little weak, then maybe it's not going to balance out quite right. And so while this setup seems to work perfectly for exclusive OR, I think maybe we need to take a look at a different design layout and see if we can get something that's going to mesh a little better with what we already have. All right, well, that worked beautifully on the breadboard. But as I said before, maybe this signal coming in through here is coming from a previous stage that isn't exactly as strong as we want it to be. And like I said, in order to do it properly, we would need to change this to an inverter and then re-invert that to get back to our exclusive OR. And if we're going to start increasing our tube count like that, well, I think there might be a better way to tackle this. And that's using essentially NOR logic. So here's a way that we can achieve an exclusive OR gate using just 3 NOR gates and an OR gate. So we can see that if both inputs are off, we have 2 low inputs going into our NOR gate, which means the output of it is going to be high, and a high input into these 2 NOR gates means that their outputs are low. So that's going to be a low output where our exclusive OR is. Now, if we take just one of the inputs high, that means that the center NOR gate is now outputting a low. And then the other input is also low. So we have 2 lows going into this third NOR gate down here, and that gives us a high output, which then goes through our OR gate to our exclusive OR output there. But if we take both inputs high, well, now we have high inputs into these NOR gates on the end here, which means that their outputs are going to go low, and so that's how we get an exclusive OR action using just 3 NOR gates. And we've built a ton of NOR gates up to now, so I think this is going to be the more reliable choice. So let's take a look at the schematic for it. And it looks a little more complicated at first because, well, we have a lot more diodes floating around. But it's really just 3 NOR gates with dual diodes for an OR gate at the end. And we can see that each NOR gate is built with 2 diodes coming into our 220K voltage divider, and then we have a 4.7K to the grid, and then we have a 33K plate resistor. And so the only tricky part about this is just making sure that we get the outputs wired up to the correct inputs. So I think this one should be pretty easy to build. So let's pull that breadboard back out again and give this specific design a test. All right, so we've got the breadboard flipped around now, and we've got our triple NOR set up on the breadboard here, and it's set up pretty much identically to what's shown here. However, unlike the last one, we should see the exclusive OR output down here go high, which means our LED is going to turn on the moment we turn the switch on, and it's going to remain high until both of these tubes here warm up. Because when they're cold, when the filament hasn't gotten the cathode hot enough yet, the tube is not going to be conducting. And if the tube isn't conducting, their plate is going to be pulled high through this 33,000 ohm resistor here. And we can see that both of those outputs go through our final OR gate here. So both of those outputs have to go low before our exclusive OR here will turn off. So when I flip the switch, we should see the LED turn on, and then we should see it fade out. So let's give that a shot here. Oh, hey, look at that. There it goes. The LED faded out. Awesome. All right, so that means that all 3 of these tubes should now be warm and conducting appropriately. So if I push one button, we should see the LED come on. Yeah, there we go. All right, let's try it with the other button. Yeah, awesome. All right, now if I push both buttons, the LED should remain off. Yeah, look at that. And just like the other one, we see a little flash. But yeah, when both buttons are off or when both buttons are on, the LED is off. And then when only one is pushed, we get the LED on. So this is a functioning exclusive OR gate. I'm actually quite happy with this. And I think this is the one that we're going to use. Except that 3 is an odd number of tubes to have. Everything that I've been building now has to be designed around an even number of tubes. That's because of how I run the filaments. On the actual processor that I'm building, all of the filaments are run in series and powered off of either the 24 volt supply or the minus 12 volt supply. That means that the tubes either need to be in groups of 2 or 4. I think what I'm going to end up doing on the actual board is I'm going to buffer this OR output here. So that way we have 4 tubes. It's kind of a waste, but also it's not a bad idea to have buffers wherever you can stuff them in, because that means that I get a little more reliable signals out of them. So all that's left is to take this design, add in a cathode follower buffer, and then put it on a PC board so that we can then complete the interconnect that's going to sit in between the top half and the bottom half of the processor. All right, so here's where the processor is sitting in its current state. We have our instruction register over here with some buffers. We have our skip functionality over here that essentially pulls our instruction register to 111 whenever we want to skip. We have the instruction decoder here that breaks that out into 16 individual signals. All 16 of those are then buffered and come out onto these individual pins over here. Now down here we've got our control for the input enable register, and then we have our input enable register here, and then we've got a little display board to show us what the input enable register is storing. And this is what we built last time. This was the first half of the interconnect. And you can see that the end piece here is connected to this end piece over here through a little PCB that I've got flipped upside down with some connectors on it. And so the next piece is our exclusive OR board, which is going to sit right here. There we go. All right, and then we see that we have some signals running along the top of the boards here. So I need another little board to move some of those signals across, and I've got that one right here. All right, now if I was smart, I probably would have put these 3 signals on this board and just made this one single board. I thought it would look cooler having it separate like this. It turns out it's just kind of a pain to deal with. So if I ever have to rebuild this board, I'll just integrate those into this one. Now we have a pattern going on of whenever we have one of these primary boards with tubes on it, on either side of it we have these little connection boards. And they actually sit a little raised simply because of the type of connectors that I'm using. So I've got another one of those little connection boards that's going to sit right here. So we'll go ahead and hook that one up. All right, and then coming off of that, we have some glue logic here. And that glue logic doesn't actually do anything until we start messing with the second half, with the actual arithmetic logic unit itself. So I'm not going to go into too much detail about it, but I'm going to go ahead and hook it up anyways, because I went ahead and made the board. And then just like before, we've got a bunch of signals moving along the top here, and so we need another board to move those signals across. So I've got this one here, and we end up with this interesting kind of open space here. I didn't really have anything that needed to fill this space, so it's just going to be open. And then finally, we need a connection piece and then our end piece. And I've got those two right here, so we'll go ahead and hook those up as well. All right, and there we have it. We have the top half of the processor and the interconnect that's going to connect it to the bottom half. And it looks so cool. It is huge. I believe there is exactly 80 vacuum tubes on here. And so all that's left is to turn it on and test it out. But I can't do that yet. We've been butting heads against this inrush current problem, and it is finally time to tackle that problem. Because I've now hit a point where I'm afraid to power it up because we're getting to a point where the inrush current is beyond what my power supply is capable of supplying. So I kind of hate to leave it on a cliffhanger, but I'm gonna. And in the next episode, we're gonna take a look at how we're going to handle the inrush current problem. And after we build something to handle that problem, we're gonna power this up and give it all the complete test as it's working and sitting here. We're getting pretty far along in the processor here. I think it looks absolutely amazing. I am so excited to put some power in it and just see this top half functioning. But that's gonna have to wait until we figure out the inrush current issues. So I hope to see you guys in that episode because that's gonna be a fun one. I have an interesting idea about how to tackle that. But in the meantime, thank you guys so much for watching, and we'll see you in the next episode.